Okay, so we concluded the last section by talking about trade-offs and how organisms compromise things like age reproduction, number of offspring produced, size, all in terms of allocating energy to certain attributes in order to be successful in their environment. Now we're going to talk about a couple tools that we can use to look at population growth and how populations ultimately mature and when they die. The first tool is called a life table. A life table, as shown below, is a table that shows us the data for the mortality rates for some set interval ages. From this, we can ultimately determine how much of a population is dying at certain years. So in this life table we have right here, we have a couple different columns to point out. We have age, so these are the different age intervals we're looking at. The number of individuals alive, so how many people in the population are still there, or how many organisms are still there. The proportion alive at the beginning of the interval. So this is a number between 0 and 1, 0 being that none of the individuals are alive, 1 being that all of the individuals are alive. Deaths during the interval, so how many individuals actually die during this from one age to another. And then the probability of dying during that interval. So how likely are you to not make it? So going through a couple of the columns, or a couple of the rows, excuse me. With age, we start with age 0, of course. With birth, in this population, we are looking at 210 individuals. So the proportion alive is 1 because all of the individuals are alive. During this interval, we have 140 deaths between age 0 and age 3. So 140 individuals die. So for that interval between age 0 and age 3, the probability of dying is 0.67. So about 2/3%, or 66% you have of not making it to age 3. Then from age 3 to age 6, we have 70 individuals alive. The proportion is 0.33, or 33%. During this time, we have 28 deaths out of the 70. So the probability of dying during this interval is 0.40, or 40%. Do one more row. Going from age 6 to age 9, we have 42 individuals alive at the beginning of the interval. So at age 6, that's 0.20 proportion alive. During this time, until we reach age 9, we have 28 individuals that die. And of this means the probability of the individuals that are left, you have a 2/3 chance of dying during this time. So the number of rows goes on and on all the way until the last age interval we have, which is 15. But from this can be a useful tool because looking at the age intervals like 0 to 3, we can tell that there is a lot of death that occurs early on, such as starting with 210 individuals and having 140 die. So we have a lot of deaths early on in this population, but later on we don't have quite as many deaths. We have 28 and then 10 and then 4. So a lot of deaths early, not as many later. That shows us that the individuals put a lot more emphasis on numbers game. So they're just producing a lot of individuals overall, ultimately in hopes that some will make it to sexual maturity and be able to reproduce. So that is a life table. The other tool we have is called a survivorship curve. So for survivorship curve, this is a graph that shows the proportion of individuals alive across different age spans of the population. So we don't have specific ages like 0 to 3, 3 to 5, so on and so forth. We just have the concept of age across the x-axis. And then on our y-axis for our survivorship curve, we have the proportion of individuals in the population that survive. So not how many die, how many are alive. So this will be between 0 and 1. So 1 being everybody's still alive, 0 being nobody's alive. And there's 3 general trends that we see with survivorship curves. We name them type 1, type 2, and type 3. So for type 1, that is this line in blue that starts out really high and then has a drastic drop later on in the age bracket. This is basically when you have high survivorship until old age. And then once you hit the old age, you basically have a huge drop in the number of individuals that don't make it. So for example, the giant tortoise, They have a lot of individuals that survive a very long time and are able to reproduce much later. But then once they get past that age of sexual maturity, much, much later, they drop off and everybody dies. So that's type 1. Type 2 is this middle yellow line that's the going in diagonal. This is your type 2. This is where survivorship decreases at a gradual, steady pace. So you have roughly the same amount of individuals that can die early on and roughly the same amount of individuals that can die later. The rate of death or the rate of survival does not really change. So just as many people survive, or the rate of change, for the number of individuals that survive at the beginning and the number of individuals that survive at the end is the same. So it's gradual. In this case, we have a bird as an example of this. And then type 3, that is this line in purple, is where you have high mortality early on, so a lot of individuals don't make it at the beginning. And then as the individuals that do survive reach maturity, they are more likely to survive. So in this case, we have our mackerel that don't survive those early years, but through a numbers game, those individuals that do make it do survive the overall course. So in this life table example, where we had 210 individuals starting and 140 die at the beginning, that would be a perfect example of type 3, because we had a lot of people at the beginning and most of them die off, and then those that do survive tend to make it. So type 1, type 2, and type 3 are those big survivorship curves. So now we're going to talk about aging and how this relates evolutionarily into biology. So typically we don't really think about aging a lot in terms of science, because typically as humans we kind of think that we have, with medicine and with technology, we've sort of skirted aging and pushed that line back. But aging actually does have a big biological relevance. And generally we think of aging as the gradual breakdown in machinery. So, our organs don't work quite as well as they used to. Our skin gets wrinkly. Our immune system isn't as robust as it once was. All this sort of has to do with aging, as we know it in the medicine side of things. But from an ecology population perspective, aging is all about the increased risk of dying. So as you get to a higher age bracket or age interval, you are more likely not to make it, is the idea in ecology. And depending on how you actually, or what organism you actually look at, impacts how you sort of assess aging. Because not every organism lives the same amount of time as another organism. A couple of examples I have below. Humans can live anywhere from 100 to 120 years, depending on if they have good health and everything. However, bristlecone pine trees can live for thousands of years, which is much, much larger than humans, and their sense of aging is on a different scale than ours. Same idea if we look down here with rodents. Rodents only live 2 to 5 years, which is way, way less than humans, but on a much smaller scale. But we, of course, can assess aging relative to a rodent versus relative to a human, relative to a pine tree cone. But the idea is that regardless of what scale you're looking at, when you're looking at aging, you're looking at the risk of dying. So ultimately, why do organisms actually age? And this actually ties into natural selection. So we know natural selection is that the environment is selecting for certain traits that fit and allow the organism to produce viable offspring to the next generation. And this idea of aging actually has to do a little bit with mutations. So with mutations, we know that that's a change in the DNA, which produces some different DNA sequence, which produces a different DNA, which produces a different RNA strand and then a different protein. So when we have mutations that cause individuals to die early on, such as at age 10, before sexual maturity, in the case of humans, that is not going to be passed on because that individual didn't make it to sexual maturity. Or if they did, they didn't have time to pass on their genes, most likely. So ultimately, that gene that caused that early death, as sad as it may be, isn't going to stay in the population because that individual didn't reproduce. On the other hand, though, individuals that have mutations that cause them to die at something like 150 or even 50, 70 or so on are much more likely to be passed on because that is way past the age of reproductive output and sexual maturity. most likely those individuals have had children, and those children would have inherited whatever genes ultimately led to the death of the person at a higher age past sexual maturity. And this is because natural selection actually weeds out the alleles that cause sickness and death early in life. Because those individuals die, they don't pass on their genes. Ultimately, it's the mutations that cause sickness and death and the shutdown and dysfunctioning of the body after reproduction that actually get passed in generations. So interesting sort of look at things on how natural selection impacts aging. So with aging, what ultimately determines the average longevity in different species? And the big idea with why some species live very short lives and why some species live very long lives, such as this rodent right here about to be snatched up by an owl, or this tortoise right here, has to do with what's called the hazard factor. And the hazard factor is the risk of dying from some sort of external factor. External factor could be something like a predator, it could be something like disease, something like competition, some outside condition that doesn't have to do with genetics and the own organism's health. So if you have a high hazard factor, you're going to most likely die very early on in your life. If you have a low hazard factor, you're going to die much later on in life. And that's going to feed into your different reproductive strategies. So if you have a low hazard factor, meaning you're not going to die early on in life, you're going to live many, many, many years, you're going to favor later reproduction because you have time to invest in growth, and getting bigger, and ultimately making sure that you don't ever die or die in a short period of time. So you can delay reproduction and put more energy into it in order to produce successful offspring. That's one method. And because they have later reproduction, they ultimately have longer lifespans. If you have a high hazard factor, meaning that you die very early on in life, you're going to favor early reproduction because if you're only living 2 to 5 years like a rodent, you're going to want to make sure that you have mated with a female or mated with a male and produced offspring and continue your lineage. So ultimately, this type of reproduction is going to lead to a shorter lifespan. And the one caveat we have with longevity and reproduction is environment can actually influence some of these relationships between when individuals reproduce versus when they actually die. Perfect example of this we have is when organisms live in captivity versus living in the wild. So organisms that live in captivity and have a lot better food quality, a lot better access to food. They have doctors and veterinarians that look at them for disease and any illnesses so that they can live a much longer life and they may not have to reproduce as early. Versus an organism in the wild that has to contend with all these density-dependent factors, competition, disease, predation, that are going to cause them to bump up their timetable in terms of when they reproduce. Okay. So another tool we look at population growth and looking at birth rates and death rates is called an age pyramid. So the idea behind an age pyramid is that we can basically break down all the age intervals from a life table and basically stack them on top of each other and see how does the birth rate look, how does the death rate look, how does the population change from interval to interval in a more visual depiction. The way we do this is we break what's called a cohort, and these are just brackets of age groupings in a population. So examples of cohorts, like when you take a survey and it says how old are you, and it won't ask for a specific number. It'll ask, are you 5 to 10, 10 to 15, 18 and above, 35 to 60. Those are cohorts. They're looking at age groupings for a population to get a sense of where you sort of fall in your lifetime. So look at some examples of these life tables. We have 2 examples of 2 different countries, Kenya and Norway. On our x-axis, we have the 25th population in millions, so the 1 million, 2 million, 3 million, 4 million. In this case, population in thousands, so 50,000, 100,000, 150,000, 200,000, etc. And then we have all of our cohorts, so 0 to 4, 5 to 9, 10 to 14, so on and so forth. We have it all broken up. Our females are in our red and our males are in our blue. So with our example with Kenya, we see that in these lower age cohorts, 0 to 4, 5 to 9, 10 to 14, the base is very wide. We have a lot of individuals that are alive at this point, which indicates a very high birth rate because we're having a lot of individuals introduced into this population. On the other end of the lifespan, we have things like the 70 to 74 cohort, 75 to 79, 80 to 84, et cetera. We see that we don't really have a lot of individuals surviving. There's barely any. And because this thins out so much, we know there's a very high death rate. Not that many individuals are making it to these higher cohorts and ultimately surviving. So it thins out a lot up here, despite having a wide base. So ultimately, from this age pyramid, we can tell that there's high birth rate, high death rate. So a lot of individuals coming in, also a lot of individuals coming out, or leaving the population because they're dying. All right, and then with our example on the right with Norway, we have, again, very wide base, so high birth rate. And then we have it pretty much stay pretty wide until we get up into the 70s, 75s, et cetera. And naturally, it does always thin out with death rate because aging does increase likelihood of death, but it's nowhere near as thin as it is in Kenya. So we have a much slower death rate overall. So we have more individuals being born, so high birth rate and lower death rate. Another example we can do with age pyramids is looking at one specific cohort over a period of time. So in this example, we're looking at the baby boomer generation. And for those of you, for a little history recap, the baby boomer generation was the offspring that were produced when the soldiers from World War II came home. They had a lot of babies with their wives, produced a very huge population explosion during the 1950s. And ultimately, this bracket, which we see in yellow, represents all of the cohorts that are of the baby boomer generation. So that's the 15 to 19 through 30 to 34 in yellow. So the idea is that we can actually track this this group, this generation, over time by looking at multiple age pyramids. So in 1985, we see they're the 15 to 34 group. Then in 2000, they're the 30 to 49 group. And then from 2015, 49 to roughly 65 group. And the idea is we see that this group actually is wider than a lot of our other cohorts. So the generation that came after it and the generation that came before it were both much smaller. So we have a huge population explosion during this time, and it keeps moving up because we have better advances in medicine and technology. So these individuals are surviving longer. And ultimately, they are reaching retirement age, which creates socioeconomic problems in that we don't know if our Medicare or Medicaid system is going to be able to support these individuals because they are so much larger than the system originally anticipated because of this historical event that occurred. So a cool example we can see of looking at one specific generation across multiple age pyramids. Okay, so we talked about life tables, survivorship curves, and age pyramids. And the last tool we're going to look at is a model that's called the demographic transition model. So with population growth, we know that not every country has the same level of growth and death as one another. And countries have tried to control for this in terms of limiting the number of offspring individuals have had or creating other restrictions potentially. Historically, we found that these don't work out very well in terms of trying to control the population. But something that does work well and has been seen sociologically is called a demographic transition model. And this is the idea that as countries move from developing to more industrialized, the population will actually level off and slow down. So in this graph below, we have birth and death rates on the y-axis as well as population growth, and then time on the x-axis. And it's broken into 3 phases. So a slow growth period, fast growth period, and back to a slow growth period. So the way this works is that in yellow, you have your birth rate, in purple, you have your death rate, and then in green, you have your overall population growth rate. So how fast is the population growing overall? So in our first phase, number one is slow growth, and our birth rate is high in yellow, way up here. Our death rate in purple is also really high, way up here. So we're having a lot of people come in, but also a lot of people leaving the population. So ultimately, our population growth rate is very low. And this is very indicative of developing countries that don't have as efficient food systems or efficient medical care. We have these high birth, high death rates. Then, as we transition to a more industrialized country, as we start to move from a developing country to industrialized, getting better access to food, better access to medicine, so on and so forth, we see that we have still a high birth rate, but also now that we have better medicine, better food, a lower death rate. So ultimately, the population is actually very, very high in this instance because a lot more people are being born, but not as many people are dying. So a lot of the focus on controlling population growth has to do with countries that are in this area with fast growth, where they have started to industrialize, but we need them to move into step 3, which is the slow growth phase. So as these countries that have become begin to industrialize, become more and more industrialized, they have higher levels of education and employment and much better healthcare. Ultimately, the birth rate will drop much lower, and the death rate will also drop much lower, but overall, the population growth rate will be much lower overall and much slowed down. So we've seen this in successfully instituted in a lot of countries just historically. So Japan, Australia, the United States, and Canada have all completed this demographic transition and ultimately have a much lower population growth rate than countries that are still developing, like Mexico, Brazil, and Southeast Asia. So the idea is that by investing resources and time and money into these countries and their infrastructure, we can ultimately move from the fast growth phase, where the population may be going too high too quickly, and slow that down by having better access to medical care, better education, more employment for the citizens. All of those impact the population growth. So, like I said, health, wealth, education, all ultimately lead to reproduction in the birth rates. So lastly, I'm going to talk real quickly about human population growth. So as of right now, in 2011, we hit 7 billion people, and it's continued to grow exponentially higher and higher in the billions. And there are a lot of models predicting how high human population will grow, but we're not really ultimately sure. And that is because of a couple of factors that are unique to humans. Because humans have a lot of ways that they can manipulate their environment and their surroundings, we don't really know what the carrying capacity is of humans. So we talked about at the beginning of the chapter, or this lecture, we talked about K. K is the carrying capacity, the maximum number of individuals that a population can hold. However, with humans, because we're able to manipulate our environment so much more efficiently, we keep sort of pushing that boundary of how high K can go. So a couple of reasons for this is that humans can pretty much live anywhere. We can expand into whatever habitat we want because we can build shelter and we have air conditioning and heat and all these things that can make us survive in areas that most likely if we didn't have those things, we wouldn't make it. So we can pretty much live anywhere. Additionally, we are able to utilize land so much more efficiently. So we're able to, with all the current agricultural techniques, fertilizer, biotechnology that we learned about in the previous chapter, we can produce a lot of food even if we don't have as much space to produce that food with. So we sort of figured out creative ways to get around that. So we can keep producing more food to feed more mouths. And then lastly, we're able to live at much higher densities. So many of us have lived in a city or around a city, or many of us flock to a urbanized area. And that increases the number of people that live in a small space. We found ways to get around this small amount of limited space with things like investing in health. So we have healthcare, and we have advances in engineering, so we can actually fit all of these people into this small space and not be so spread out. So we've figured out ways to change our environment and manipulate it for our benefit. But ultimately, these raise questions about how many resources do we all actually need? While we can manipulate the environment in all these ways, how does this contribute? So what we have is called the ecological footprint. An ecological footprint is the amount of resources either an individual or a country uses. You can look at an ecological footprint on a per capita rate, which is per person, or per country rate. So how much food are we eating? How much waste are we producing? How much medicine do we need? How much space do we need to take up? All of these sort of contribute to ecological footprint. And the distribution of resources is most certainly unequal. So some countries have much more access in resources than others. So the United States has way more many resources in terms of food than other countries that are still developing. And because of that, our resource use is very uneven, and so is the distribution of wealth. So some countries, again, like the United States, countries in Europe, Japan, etc., they have much better access to healthcare because they're much more developed, much better employment, education opportunities than we see in other areas that are still developing. And all of this raises the question of how high can the human population actually go? So the human population is over 7 billion, rapidly approaching 8 billion. We're adding about 80 million people per year. So ultimately, people don't really know, are we going to be able to continue to support this rapid growth? Do we need to really continue to push the demographic transition model where we're getting countries to be more industrialized so we can slow that population growth? Is it going to matter because eventually we're still just going to run out of room anyway? People aren't really sure. There are estimates that the Earth has already reached its carrying capacity. There are estimates that go up to 11 billion people, which I believe we're going to reach by 2050, 2060, depending on current models. So all these sort of raise questions about what is the human race actually going to do when we reach that point. More of a philosophical question than a biological one, but based on biological relevance. But that is all we have for chapter 16. So I will see you all next week.